Okay. Yes, with that, we can get started. So as Gabe said, if you have some questions in the chat as I'm talking that are maybe more minor, you can write them down in the chat. And if someone else knows the answer, you can answer. But otherwise, I think at each different at the end of each stage of the pipeline, I'm probably going to stop and ask all of you if there's some pending questions to answer, if they were not answered. Otherwise, if there's a more pressing question, you can always interrupt me and I'll do my best to answer them and manage the time continuously. So it's I'm not sure exactly how long this is going to take. 2 hours might be short, depending on the interruptions, because for those that have gone through the entire pipeline, it's pretty long. There's many aspects to it, but hopefully we get through. I'll do my best to manage the time. With that said, welcome to this RABIES workshop. My goal today is going to be to really take you through all of the different aspects of the pipeline, give you some conceptual understanding of what the software is doing at each step, and then give you some insight into how it looks like from a user perspective when you execute the software and when you use the outputs at the end, and how eventually you can try to make decisions to tune the pipeline to really give you best quality outputs. So RABIES is a open source software that we've developed in the lab over the last couple of years that's really aimed at standardizing image processing for rodent fMRI images. I hope this is going to be a useful tool for the community at large to improve reproducible practice and make, I guess, rodent fMRI research much more efficient and easy for the new users that might not have necessarily a computational background. So here, what I'm showing here is the beginning of the pipeline, which begins, of course, with pre-processing of the raw images to mostly register them properly in a command space, give you a parcellation. I'll cover the details later. Together with the pre-processing, there's automated quality control images that are generated, and they allow you to effectively check whether each crucial steps in the pipeline have been run effectively and if there's errors of registration. And this workflow has been tested out a range of different data sets in both mice and rats, as documented in my current preprint, or more recently by Johannes' multi-site rat study, where he used even more data sets than me. And we've achieved very high registration quality after tuning properly the workflow. So hopefully you can manage almost any possible kind of images you might give it as input, if it's properly formatted to begin with. But now, following pre-processing, there's also some confound correction strategies that are available, inspired from the human literature. It should be able to cover most of the pretty standard correction strategies in the literature. And then there's also some basic resting state connectivity analysis that are made available. Of course, it doesn't include every possible analysis because this is a very broad literature, and the goal is not necessarily to cover every possible analysis. If you want to do very advanced analyses, you'll have to work it out from the RABIES outputs. But for basic usage, you might find what you need in there. And finally, a last aspect of the pipeline that's maybe a bit more innovative compared to standard image processing software is data quality assessment, where essentially by developing RABIES, I try to leverage the human literature on how to assess data quality and apply these tools to rodent images in many different sites to characterize the confounds that we find in these kind of data sets, and then develop certain recommendations for how you can hopefully ensure that your analysis down the road is not corrupted by confounds. And so this is divided first by a scan level observation approach, followed by more a group level statistical report that I'm going to cover later. So first, I'm going to go through the pre-processing in detail. First, a few comments on the inputs format. So as many other neuroimaging software, RABIES follows the BIDS formatting standard. I won't go over too many details on the BIDS format. They have their own website with their own documentation if you want to learn everything about it. Otherwise, as it pertains to using rabies, there's some more details on the online documentation for rabies. But overall, giving you an example here, it's a nested folder structure that looks like this, where within your overall data set, you will have your subfolder for each subject, followed by a subfolder for each session, and then one for anatomical and functional scans, followed with the Nifty files that has the proper naming convention. And maybe of interest to you, if you have some raw Bruker files that you want to convert to Nifty, what we're using in our lab is this Bruker raw package. You can check it out. It might even be able to handle a direct conversion to bits, although I haven't been able to make it work out myself, but maybe other ones in my lab have. Anyway, they're supposed to be able to do that in principle. And otherwise, we have also a lab wiki that describes how we're doing this if you're interested. So that defines really the images that you're providing as input from your data set. And the other important input to consider is going to be the reference template together with the parcellations for that template. So I'm showing here below the default mouse template that's already available when you install Rabies, where the required inputs that you really need to specify are a proper, of course, structural template together with the whole brain mask. I'm going to emphasize whole brain mask because recently I ran into a problem with Francesca where there were some missing voxels inside the brain, and we realized only much later at the analysis stage that it was causing some problems for quality control. So there needs to be no hole in the brain mask, otherwise it creates inconsistent brain coverage between subject, and that leads to problems. So these are the two required inputs. But together with that, if you have access to these masks, you can provide white matter, CSF, or vascular masks, which are useful for the confound correction stage. If you don't have them, you can instead just provide the brain mask multiple times just so that the pipeline runs, but you just need to be aware that you can't rely on these masks later on for confound correction. And finally, you can also provide a whole brain patient if you want to do whole brain connectivity analysis. So together that defines all the inputs for the Rabies pre-processing workflow. Now, the first step in the pre-processing will really consist of trying to align the different scanning session in a common space. And this is going to be done with the structural images primarily. If you don't have, I want to know that if you don't have structural images, you can still run the pipeline only with EPI images, but ideally, if you have the structural images, they will do a better job of really aligning your different subjects. So that's recommended. But there's a way to run it only with EPI scans as well. But if you have structural images, the first step will be to correct for inhomogeneities in intensity in the scan. So when you acquire a raw image, often case, especially if you have a surface probe, there's going to be an intensity gradient from the top to the bottom of the brain in the raw image, and you need to correct for that before you can register properly the image. So that step will carry this out to obtain a homogeneous image that can be registered. Then the different structural scans of different sessions can be co-registered together to what we call an unbiased template that's going to be generated from your dataset images. Now, the reason why we do this instead of registering directly to the atlas is that this provides a more robust reference for registration because it's going to be an image that's similar to your dataset. Whereas the external template might have different acquisition parameters, it might be a histological atlas in certain cases, and that can lead to more registration errors between the different subjects. So having this intermediate template helps have a more robust registration, basically. And after that's generated, then the unbiased template can itself be registered onto the common space atlas to finalize the common space alignment. Now, after the structural steps are carried out, the EPI itself can be pre-processed. Similarly, first with the inhomogeneity correction step, where it works in the same way as the structural scan, where we want to obtain a intensity homogeneous image in the brain. And then that image can be registered to correct primarily for susceptibility distortion in the EPI image. Since when you acquire a raw EPI scan, there's going to be some anatomical distortions, such as these that I'm highlighting there. And to recover the proper geometry of the brain, you want to do a nonlinear registration of your functional image onto the structural image from the same session. So this is a registration that happens within subject within the same scanning session. And now the last registration step of the pipeline is head motion correction. Now this is happening within each functional image across different time frames. So as many of you know, head motion is a big problem for functional images because if the brain is shifted in time, then the voxels don't align together, and that can create many analysis problems. I'm going to touch a bit more on that later. But essentially, you will register, RABIES will register each time point to the median image across time so that you can estimate at each time point the relative position of each frame in terms of 3 translation or 3 rotation parameters relative to that same reference. So by doing that, you obtain essentially motion across time. And you can derive from these parameters what's called frame-wise displacement, which is essentially quantifying the distance that was, how much the brain has shifted to the previous frame. So it's like the temporal derivative of these motion parameters. And that gives you where in time there was significant motion events. So these are all computed from that registration step. And the final step will be to apply all of these transforms that were computed in one shot to each frame. So essentially, the transforms computed for head motion realignment, distortion correction, as well as resampling either to native or common space will be applied in one interpolation on each EPI frame. It's done in one interpolation to avoid having multiple resampling of the fMRI image, which can cause more loss of the original data. So we really want to minimize the number of interpolation. So they're all combined together in one shot here. And that finalizes the pre-processing. A few additional notes, there's other options that are also available outside of this core pre-processing, mostly adaptations from the AFNI software doing slice timing correction, despiking, or autobox cropping of the image. And another option you might be interested in is customizing resampling resolution for your pre-processed scans, where you can decide to resample it to a more fine resolution, maybe if you're doing common space, to reduce how much data you've lost by the resampling interpolation. And that covers together the overall pre-processing steps. And if you're interested in seeing all the detailed options, go to the online documentation. There's all the details of the command line interface you can find. Now I'm going to show you a bit more how the basic syntax look like when you're executing the pre-processing. And all the details are laid out, again, in the online documentation for further consultation. But the basic installation for RABIES, it can be installed with pip install in your local environment. If you can manage all the dependencies, I'll come back to that in a moment. But from your terminal, the syntax for running RABIES preprocessing will look like this, where you first specify RABIES, you want to run RABIES. Then P multiproc here is a option that specifies you want to run the software in parallel. I'll detail these out a bit later. Then you need to specify preprocess, which is at which stage of the pipeline you are. Here you're doing preprocessing. Then you provide the input directory and the output directory together with your further options for preprocessing. So it's relatively straightforward. Then doing that, if there's no errors in file format, it will run and execute the whole pipeline. However, the way we really want to recommend installing the software is rather than with pip install, it would be with a container. Because with a simple pip install, then you have to manage all the dependencies carefully. And you might not have exactly the same computing environment on your, either in your lab or on your laptop. And so there might be, it's more risky to have more unexpected errors that arise or inconsistent outputs between different computing platforms. So a solution to that is to have containerized installation, which can be done with either Singularity or Docker, where a container is essentially a small operating system that has all of the dependencies installed internally together with the RABIES software. So these are the command to install an image of a containerized image of RABIES that you can then run. And then the syntax is a little more complicated, but there's really one main difference in the syntax, which is that you need to provide these binder flags here. I'm showing the example for Singularity, where you need to relate the path to your local folder file system to a folder path inside the container. So here I'm showing an example for the path to the input dataset that I want to pre-process on my local system. And then inside the container, I'm calling it the inputs like this. And that means that then when I'm running pre-process and specifying the inputs, I need to call it the same way that I specified it earlier. So this is the overall syntax. Everything else is just adding more specific options for your pre-processing depending on your needs. So in terms of managing computing resources, this is where you have, for instance, this P option where you want to run it in parallel. When you're running a container, there's only two options you can really run, either linear, where you're running only one process at a time. This can be done if you're just testing things out and making sure there's no bug. But for running it effectively in parallel, you'll want to use multiproc, which will use every CPUs available, at least by default. If you want to manually specify the number of CPUs the maximum number of CPUs you want to use, you can change this local thread parameter. And if you run into memory errors, you might be interested in changing this scale memory parameter, where if you increase the scale, you're saying to the pipeline, you can be able to manage even more memory requirement. Or if you're getting errors, you'll want to reduce the scale of these parameters to have a lower threshold on how many processes it's going to allow to execute, depending on your memory resources. And these are really the main parameters to look at for managing computing resources. Now, after it runs effectively, you have a bunch of outputs generated in your specified output folder. For preprocessing, it will likely look like this, where here this main workflow folder is the biggest one with all of the internal intermediate files that were generated during preprocessing. But unless you're a developer, you can ignore this one. The main files you'll be interested in are all located in these data sync folders, or the quality control report that I'm going to cover later, or also the log file here, which I might ask you to provide me if there's a bug that you want help on. So I'm going to give you more example for the bulk data sync, which gives you really all of the preprocessed time series and the labeled files. So in most cases, that's what you're going to be interested in. Inside the data sync folder, there's a bunch of subfolders for different file types, covering, in this example, is only command space outputs that were provided, where the first one, command space bold, is your preprocessed time series. Inside the command space bold, it's going to be subfolders for every different subject, and there you can find the generated Nifty files that were accurately preprocessed. And otherwise, the other very important folder that in practice you will definitely always look at is the quality control report. So something I forgot to mention, if you're just going to use RABIES at the next stages, let's say the confound correction, analysis, and so on, and you're not using these outputs directly yourself, you might not even need to look at these data sync folder. But the one you definitely need to look at is the quality control report, where you need to make sure that it was carried out properly. And inside this report folder, there's these subfolders that describe different aspects of the preprocessing pipeline. The very first one, template files, is simply going to be a PNG image that just shows the template files you provided. This is really just a display of your inputs and can be useful in some instances for detecting where there was a problem with the original inputs. So that's the only reason why it's there. But now the first actual pre-processing step you want to look at is the inhomogeneity correction of the structural scan, where the image is going to look like this. First, with showing you the raw image on the far left with the clear bias in intensity present. And then following that, there's going to be an initial correction, where the initial correction was carried out with a kind of coarse mask that was just generated based on the intensity profile of the image, but it's not necessarily a very accurate correction. It might not be sufficient. And that's why there's a subsequent registration step within the inhomogeneity correction, where the anatomical mask will be registered onto your reference template to hopefully get a good brain mask that can then be used to orient a final inhomogeneity correction and obtain the final correction on the right. So most of the time at this step, actually what you'll want to check is how good your brain mask was. That's really the main aspect that's going to determine the quality of your inhomogeneity correction down the road. Next, after the inhomogeneity correction, you want to make sure that the registration to the unbiased template was carried out properly. So registration quality control outputs look like this, where at the top there is the moving image and at the bottom the target image for registration. And in this case, the top image is going to be a single anatomical scan, and the bottom is the template that was generated. And the highlights in red delineates the boundaries of the image for the boundaries for the opposite image. So actually, in this example, they look almost the same, but the boundaries here at the top actually are derived from the one at the bottom. So it helps to just visualize that the boundaries are well aligned between the two images. The next registration step is the Atlas registration, where here you have the generated template registered onto your external template. And then next, we can move on to the functional preprocessing, where here for the inhomogeneity correction, it's going to be exactly the same principle as the anatomical image, where you'll want to make sure the correction was well carried out with a good brain mask. And the final registration step is then going to be the EPI to ANA folder, which is the registration of the EPI scan onto the anatomical scan of the same session for susceptibility distortion correction. So in general, when this very last step is successful, actually, it means that every previous step was likely to be quite successful because they are interdependent. I'll show you in order of execution the different registration steps. And ideally, you want to go in that same order to make sure that the later ones, if they fail, you understand that you can relate it back to some previous error and know what was the real cause of the error. Because if there's an error at this stage, it could be actually driven by any of the previous stages that went wrong. And the final output in this QC report is not necessarily a step to really quality control. It's more of a visual, it's giving you more of a visual intuition about the temporal profile of your scans. And it can be useful in certain instances. So first, it shows you the translation parameter and the frame-wise displacement that were computed. So you can get an intuition of how much motion there is in your scans already. And the next one is the standard deviation at each voxel. So it's showing you the distribution of signal variability, which can be useful in detecting actually a range of artifacts or compounds. You'll see examples later. And finally, there's the temporal SNR. Just to give you an example of how this signal variability profile can be useful, recently a RABIES user actually pointed out a grating artifact that he detected from this report when using slice timing correction with EPI, where he saw that computing slice timing correction was introducing these slices at the front and the back of the brain. And he figured out that it was due to the nonlinear application of the slice timing interpolation that we were using in RABIES. And if we allow the flexibility to choose other type of interpolation, we can correct this issue. So that's soon going to be corrected. And this doesn't mean that every slice timing correction is wrong, by the way. It was specific to this particular data set. But I'm just giving you an example of how it can be pretty useful to detect certain early failures in the preprocessing. So that's my last slide for the preprocessing stage. And it's the one really that's unfortunately a little bit harder to standardize. And you have to gain a bit of experience by playing with registration and detecting errors, trying different parameters. And that's where you deal with problems when it doesn't go well. So I'm showing you a very drastic example here of a failed registration where the brain was completely out of the frame, but the registration won't necessarily be as drastic as this. They might be more subtle, maybe just part of the brain here on the, on one of the corner is misregistered for some reason, maybe because of a bad brain mask. And so in those cases, you need to review what is your issue and what might be a good option to correct it. And if you want to read, take time to read and think more about this, I recommend reading through that documentation, which has more detail than what I'm going to cover right now. But just to give you a bit of an overview, so at the inhomogeneity correction stage, if you have, for instance, an incomplete bias field correction, you corrected part of the image, but it didn't go through all the way to the bottom, for instance, there's an option that increases how stringent the inhomogeneity correction is going to be. If you get some partial registration or a subset of your scans have masking failure, there's these robust InnoCore options, which are essentially going to compute the unbiased template generation during the inhomogeneity correction step. So it's a more computationally expensive step to run, but it ends up being the most robust way to generate very good quality masks. So if you want to really have a top-notch masking quality at this stage, you might be interested in considering this option. Otherwise, if some tissue outside the brain is causing weird inhomogeneity correction with bad intensity distributions, and then your image is misregistered outside of the brain, you might want to consider cropping these images either before RABIES or using these automated options, or you might want to increase the at which we compute the initial correction. So we're gonna just go back to that image. So here at this initial correction stage, I said there's a initial mask that's computed based on the intensity profile of the image. But if you have tissue outside the brain, such as this, that's causing you error, maybe you want to increase the threshold for that mask so that it's really more focused inside the brain and have a more precise initial correction. So that's what this option can do. And otherwise, if you keep having many failures, you might need to reduce how good the registration method is from nonlinear to affine, rigid, or no registration at all in some instance. Otherwise, for the other registration steps for actually aligning the column space or distortion correction, the main thing you can manipulate is going to be whether you use masks that were inherited for the inhomogeneity correction step or not. So if you have very good quality masks that were generated from inhomogeneity correction, you can use these masks to help registration with this option masking equal true, or this more stringent one, brain extraction, where you're literally gonna constrain registration to ignore all voxels outside the mask. So that's very good for matching brain edges precisely, this option, but you need to have good mask, otherwise it's gonna completely fail. So if you have more questions on this, I invite you to consult the documentation. If that's not enough, you can raise discussions on the GitHub page. I think that's a good place for this kind of discussion. So that's it for pre-processing. Is there any question that could be addressed at this point? I don't see the chat.
I've been taking care of the chat. Anybody have any
taking care of it?
Any verbal questions anybody wants to bring up?
Okay.
We'll say going once, going twice, sold. Continue on.
All right. Then let's move on to confound correction.
Sorry, I raised my.
Yeah, sorry, I didn't see the hand until later. Go ahead.
No, I was slow with my mouse. I was just wondering, I think we had a meeting with you guys a little while ago about, I think it was Ant's motion correction respecting the hierarchical structure of the cluster that we're trying to run it on. Has there been any progress on that?
So no, I haven't had time to address this issue.
Okay.
I think our conclusion for that issue was that it's indeed not very sensible necessarily the way it's doing it, but I don't think it changes much for the computational efficiency necessarily, because it's like instead of, I think the problem, if I remember, is instead of taking all of your different CPUs on one registration, one head motion correction step, it was spreading it out across different scans, which means that it's just going to be more spread out when it's doing it, but it's not actually taking more time.
Yeah, from my perspective, I would think as long as you have enough memory, the total time ends up being the same. I think you can end up simulating that you have total number of work to do and total number of CPUs to do. So as long as you don't go over your maximum available memory, the total amount of time spent should be the same. It just one feels like no progress and the other one suddenly is all done.
Okay. Thanks.
So in terms of, if the question is to save computational time on head motion correction, there are ways to scale down the registration quality for that step, but I would recommend being careful if we go down that road. We can have another discussion about this in private for your particular data set. But yeah, I feel like the main trade-off, if we go faster, is that it might be a more poor registration and a poor head motion correction. So these are things to consider. Otherwise, if there's no question, I'll keep going. But like I said, you can interrupt me if there's a pressing question that comes up as I'm talking. So the topic of confound correction can become definitely pretty complex and convoluted. So here I'm gonna, my goal is definitely not to make a literature review on that topic. There's a lot of very good literature on that and very good reviews on what are the different confounds to look at and what are the range of strategies. So what I'm gonna cover here is just the main type of correction steps that you should consider that are available in RABIES and how they are executed within the pipeline. But just to give you a very quick intro, as many of you probably know, since BOLD is an indirect measure of activity, a neural activity, there's other sources that can corrupt the window we're trying to get onto neural activity. And the main one that's been discussed really is motion. We've already said that during pre-processing, we need to realign the images with registration. But in fact, even that is not enough because the intensity profiles of the EPI image get also distorted by motion, even after you've realigned it. And in fact, it leads down the road to intensity correlation across time between different voxels, such as described in that great paper by Sutter-White. And since with connectivity analysis in particular, we're actually looking at temporal correlation between voxels, this is a very serious confound that we need to account for. And otherwise, there's a range of potential physiological influence that can also lead to fluctuations in BOLD that don't have a neural origin. And we need to be aware of those and try to mitigate them the best we can. And that's where really there's a range of different extract correction strategies onto the time series that have been developed over the years. And I'm going to go over the four main ones you might want to consider in RABIES. The first one is frame censoring or scrubbing. where essentially we identify frames that are highly corrupted and should be discarded altogether. The main way to do that is with the frame-wise displacement that I've described earlier, where you can select a threshold where when there's been too much motion at a certain time point, you remove that frame and also the neighboring frames to completely discard the potential impact of these high motion frames on your analysis. And this is partly because, as some of these papers have documented, we unfortunately can't completely correct the motion in some of the very highly corrupted frames. So that's a very good solution that I recommend using if you have high levels of motion. And sorry, I forgot to describe what this is here. So at the top, this 2D matrix is called the carpet plot, which shows all the different voxels across time. So essentially what you're visualizing with this display is your entire time series across time. And with that, you can detect, for instance, global signal fluctuations where many voxels have shifts in intensity, which are usually going to be confounds. Like in this case, there's some clear intensity fluctuation happening at the time of motion that you want to correct for. Now, the second strategy, which is really I believe the oldest confound correction strategy, which is confound regression. And this one is really used in almost any resting state fMRI paper. So you almost inevitably will do some of that, at least, where essentially we're defining a set of nuisance time course or regressors, such as the 6 motion parameters that can describe the impact of motions, and regress these with a linear regression onto the time series at each voxel. And I'm showing you an example here where we have the raw time course in blue. We fit these regressors to remove the variance explained from these regressors in red to obtain what should be a cleaned time course in orange post-regression. And I'm going to cover some other regressors that you can specify in RABIES. The other important step is temporal filtering in the frequency domain. So most of you will also be familiar with this, where you will want to consider doing a high-pass filter to remove low frequency fluctuations that are usually not related to neural activity, or a low-pass filter to remove high frequencies that tend to also be related more to physiological or motion confounds rather than neural activity. And another option that's more advanced, I won't go into the details here, it's ICA aroma. It uses a IC decomposition to automatically remove sources of signal that are associated with motion and keep the ones that more a neural source. And it can be pretty effective for removing high levels of motion. And if you're interested, I recommend reading the original paper on that technique. So how this is implemented in RABIES is laid out in a stepwise manner, and the order of the step is pretty important, actually, because if these different steps are not applied in the right order, some papers have documented that you can unfortunately reintroduce certain confounds that have been previously removed. And I'm going to detail why this can happen, for instance, with frequency filtering or confound regression. But within RABIES, the first step that's executed is frame censoring. So we simply flag which frames we want to remove. You can do this with frame-wise displacement, as I've shown, or with the DVARS metric. The DVARS metric is the temporal derivative in global signals. So it tells you, instead of where there's motion spike, it's going to look from your time series signal where there's rapid shift in global signal intensity. So they're often related to one another, and you can detect outliers with that metric to remove those frames. The next step is detrending. It can be either a linear or a quadratic detrending, but detrending is always applied because essentially we need to remove at least the mean of your EPI before we can compute analysis. And then third comes IC aroma, where you can specify either a consistent number of components to be computed in each subject, or just use a automatic estimation from the melodic ICA PSL software. And one note here on the design of these steps is that these are applied before frequency filtering because we want to maximally remove spikes in signal, either from motion or other sources with frame censoring or IC aroma, because spikes are not dealt well. Frequency filters, don't deal well with spikes. And in fact, it's been documented that they can introduce some ringing into your time series if there's too many spikes. So that's why removing all of them before filtering can be pretty important. At the filtering step, you can specify essentially at which frequencies you want your high pass or low pass. And also importantly, you need to specify your repetition time because the filters are computed based on that. Now, another important design note is that since we're applying potentially frame censoring before filtering, we end up with missing time points. And unfortunately, that's a problem that's not dealt with by classical filters. And so in this great paper by Power and colleagues, they described the way to deal with this by simulating the time series with what's called a Lomskargol periodogram, where essentially you're just filling in the missing time points while preserving the same frequency profile in your time series. And so then you can apply your filter after that to filter all the frequencies appropriately.
Thank you.
Yeah.
I have a question. So you mentioned that it's really important that you do these in this order, but also in the previous slide, it seemed that some of them were more of options such as ICA aroma.
Yeah.
So first, would there be like a reason why you might want to like skip step 3? And if so, can you still do step 4?
Totally. I was going to mention this, maybe I should have said it ahead of time, but so all of these options are customizable in RABIES. Actually, they're not applied at all if you don't specify them, except for detrending. Detrending will be always applied because you need to at least remove the mean, but all of these other steps are optional, and you definitely won't want to just apply everything. I'm going to cover a bit more on this later at the level of data quality assessment, but the way you will design your confound correction will depend on the specific needs of your data set. And right now in the literature, unfortunately, there's no ground truth for how we're supposed to correct for confounds because there's all sorts of technical problems involved. And unfortunately, it's the state of the literature where different labs have different ways of correcting for confounds, and there's no absolute protocol for how you're supposed to do this. But hopefully the tools I'm going to present later will support your decision in that respect. So after frequency filtering is confound regression. So you can specify with which regressors you want to regress among the list here. So within RABIES, the options you have are either 6 or 24 motion parameters. You can regress the white matter CSF or vascular mask signal for physiological confounds, the global signal, or using this anatomical concord technique. You can consult it in that reference if you're interested. But the reason why this step comes after frequency filtering is because it's been described in that paper by Lindquist that if you need to actually apply filtering to your regressors before applying confound regression, or otherwise you might reintroduce confounds that were regressed by the filters. So actually, within RABIES, the regressors will go through all the same steps that your fMRI time series went through, where they get censored, detrended, and then filtered before the regression. And all these details are important to avoid using some errors at the regression step. Now, after all this is done, there's a image scaling step where if you're comparing different scans, in some instances of analysis, you'd want to scale the intensity of your EPI to be comparable relatively to one another. If you do only correlation analysis, it's not that important because correlation is already standardizing your variance, so you don't have to care as much about this. But for other techniques such as dual regression that I'm going to cover, you'll want to carefully consider this option. And there's several options within rabies. And unfortunately, again, this is a stage where there's definitely no ground truth. It's actually a stage that I'm quite struggling with making accurate decision myself. So actually, if you have some experience and insight on this, please reach out and contribute to these decisions. But overall, by default, I guess the simple go-to method might be to simply scale image relative to the grand mean intensity, so that the mean intensity of your image is comparable between your different scans. That's what different papers using dual regression are generally doing, at least with the FSL group. So otherwise, then you can apply some spatial smoothing to increase SNR. You can specify the smoothing filter size in millimeter. And then finally, some other options you'll want to consider are this edge cutoff parameter here, where you can remove a number of seconds at each end of your time series when frequency filtering is applied to avoid certain artifacts. So I've taken this from that reference by Power here, where he described that frequency filters can introduce artifacts at the edge. And to be more conservative, he recommends removing a certain number of seconds at each end. So you can consult that for further insights. Otherwise, this option here, match number of time points, allow you to constrain your different scan to retain the same number of frames after censoring, because in some instance, your analysis can be affected by degrees of freedom, or how many time points you've derived, how many time points there was in a given scan. So this is a way to mitigate these issues where you can have inconsistent numbers across scans. And finally, this parameters define that you want to compute your confound correction on native space outputs. So I said this already, but only detrending is applied and every other option need to be manually specified. So in terms of execution, I mean, there's not that much more detail to go over. It's very similar to what I've already covered on the pre-processing stage, only with different names. So here you have confound correction step instead of pre-process. You need to provide your output from pre-processing because rabies will need to read these outputs. So something important to keep in mind when you run rabies at different stages is that you should not modify the outputs that are generated because they will be used at later stage. And if you remove outputs, it's probably going to give you an error. And so then with that command, you also specify where you want your new outputs for confound correction, and then your list of correction steps. The main new output you're going to get is this confound correction data sync, where you can find within that a folder with the clean time series nifty files, which is probably the main file of potential interest. So it's likely that if you're doing your own connectivity analyses outside of rabies, you'll want to use these nifty files as your input for your analysis. So that concludes confound correction. Are there any questions at this stage?
Anybody want to bring up specific questions?
I mean, if not, I'll keep going.
I guess I have a question that I would like confirmation to. So in our case, we have a mask that is a combination. I don't know if you already covered this. I apologize if you did. But we have a mask that is a combination of white matter, CSF, and ventricles. So in that case, do we need to input all of them as a confound regressors, or one is enough?
So no, you don't want to do one.
You know what I mean?
Because in your case, you would be repeating multiple times the same news and stem course, right? And what's likely to happen is actually going to be an error during the regression step because the linear regression can't deal with two time courses that are exactly the same. You get it's an error of a matrix inversion, more specifically. So it's literally a mathematical error. So you can't just provide one, and you just need to be aware and specify in your paper that you've said white matter signal regression, but actually this stands for a distance for white matter, CSF, and so on. So you just need to document it well.
Thank you.
All right, so we'll continue on.
Yep. So next, at the analysis stage, so within RABIES, I'm offering you a set of basic resting state analysis, some of the most common ones that don't require necessarily very advanced computations. If you want to do your more advanced computations, like I said, you need to use these outputs from confound correction and write your own code. And again, here, I'm not going to do a literature review on resting state connectivity analysis. There's a lot of literature on this. And so if you're not necessarily familiar with this, I recommend you reading more about it. But essentially, the basic one available in RABIES, most of you are familiar with seed-based connectivities, the classic connectivity analysis where you put a seed in a brain region and you correlate that seed region with all of the other voxels. I'm showing you an example here with a seed in the cingulate cortex here and where it's correlated across the brain. Otherwise, you can derive a whole brain connectivity matrix from your parcellation provided at pre-processing, showing the pairwise correlation between every region pair. And then there's a other family of analysis, which is more derived from the ICA approach, where the ephemeral time course is decomposed into different sources. So I'm showing you an example here of a ICA output that's giving different components that represent brain networks in the mouse. And within RABIES, you can compute a group ICA, where essentially in a group ICA, all of your different scans are concatenated together. And there's a single dimensionality reduction that's applied across all these scans to identify what are the main sources across your scans. And here I'm showing you examples of networks, but there's also going to be a lot of confound components that show up. And these will be pretty important in the later stage I'm going to cover. But now in the context of doing ICA, the problem is that group ICA only gives you a bunch of components at the group level and not necessarily scan-specific connectivity estimates. And for that purpose, there's a technique called dual regression that go from the group level ICA components to individual versions of those components. And I'm going to cover that technique in more details because it's used at the level of quality control that I'm going to cover later. And so to go from these group level priors to individual specific fits, dual regression operates in two regression steps, where first these group IC components, which are going to be a collection of potential brain networks like these two, as well as confound components like these other two examples, they're going to be regressed against the scan time series to obtain their associated time courses. And then in the second regression step, these time courses are themselves regressed against the time series to obtain a spatial counterpart. And now these spatial maps you obtain will be a scan-specific version of each of these ICA priors that you have to begin with. And so this is a way to really go from this group level component to a scan-specific version of these for every subject, and then you can use this to do your statistical analysis. So essentially, in summary, among the analysis available, there's ICA that can be done at the group level. So you can't, with these outputs, it's just a summary of your whole data set. You can't necessarily do a statistical analysis on top of that, but it's pretty useful for, of course, if you want to do dual regression, but also I recommend doing a ICA on any new data set to explore what kind of sources you can detect in your data set. This is actually a very good way to get insights into whether you can detect brain networks, how many confound there might be. So it's a good step for getting intuition about your data at the same time. And otherwise, the other three are really generating connectivity map for each individual scans. And then you can load these
into your statistical analysis to compare groups, for example. So these outputs will be generated in a analysis data sync folder, where within that folder, you can find, for example, Nifty files for the spatial map of dual regression, or CSV file for the time courses. And similarly for seed correlation map, you can find the Nifty files in this folder, or CSV for the time course of the seed. And similar formats are in either a Nifty format for a spatial map or CSV are kept. They're pretty intuitive. And again, the execution syntax for this stage is very similar to the previous step. So I won't cover the details here. So there's no more question. I'll be ready to move on to the last step. But, no, that was clear.
All right, let's keep going.
So this last stage, I will disclaim, it is the maybe less standard step or innovation in the pipeline. So all of the previous steps I've covered are pretty standard in the fMRI software. They allow you to do minimal image registration, maybe some confound correction options and some basic analyses. But often case, they don't include standards for exploring data quality in details. And with RABIES, in the context of developing the pipeline, I leverage what there is available in terms of data quality tools in the human literature, and I'm trying to make them available within the RABIES software so that we can hopefully improve our standards when looking at data quality to make sure there's minimal impact on results and that we can then better compare studies across different centers and improve reproducibility. But unfortunately, as it relates to the field of confound correction, there's unfortunately not a gold standard for how we're supposed to do this. And so what I'm going to go over here are the tools that I've developed by looking at a range of different mass fMRI data sets, observing different potential pitfalls in data quality and how we can hopefully correct for them. But these aren't by no means supposed to be the absolute way to look at or the only way to look at data quality. And if you have some discussion points or even criticism to bring up in that section, you're welcome to. And I expect this to keep evolving over time as the pipeline develops. But really the goal here is to try to, hopefully as a community over the years, within the RABIES software platform to improve our standards for looking at data quality and really improve the quality of rodent fMRI research over time. So overall, there's different dimensions to the data quality assessment within RABIES. The first one is more of a observational step. It's a bit more intuitive, and it really regards what I call a spatial temporal diagnosis at the scan level, where a set of temporal features, such as those showing here, and spatial features are generated for each scan. And the goal here is to be able to characterize in detail what kind of quality issue might be present in your scan, and then try to infer what might be a good correction strategy or how they can impact your results. But then after this observational step, we need to more formally quantify how potential statistical analysis might be impacted by data quality issue. And that's why there's a subsequent report, mostly at the group level, that aim to summarize how your data quality might be impacted to really complement the observational nature of the first report. And then after you've gone through the different steps of data quality assessment, then if you have certain issue, you get to the step of troubleshooting. And I'm going to end with a few comments on this at the end. But I'm first going to go through in detail the scan diagnosis step. So this scan diagnosis report can be a bit intimidating at first because there's a lot of different measures to kind of digest and go through. But over time, once you kind of get an intuition of what each of these parameters are and how different scans compare, it can really help a lot to go through the scans. And there's definitely a bit of a learning curve, but I really encourage you to get used to looking at this report, where here I'm showing you a set of temporal features for a good quality scan that has minimal confound. The first one is the carpet plot showing all of the time series I've already described earlier. It's followed with the 6 motion parameters together with frame-wise displacement, and in blue, the standard deviation, the temporal derivative of global signal, or DVARS. And then that's followed by the signal time course for different anatomical masks, as well as the variance explained by the confound regression step. So in purple, it's the R square, so the ratio of variance explained by confound regression at each frame. And then in red, it's the actual amount of variance that was corrected during that step in your scan. A last important temporal feature that's also included in the report comes from dual regression. So something you'll have to provide to compute this diagnostic report is some ICA maps so that dual regression can be computed. And I'm going to give you more details on how you can do that later. But essentially, what's going to be important is to classify which components are corresponding to brain networks and which ones are corresponding to confounds. Because these different categories will be combined by taking the mean amplitude of their time course to obtain in blue a representative time course of the networks and in orange of the confounds. And that's a very useful feature to get an intuition of how your network time course might be correlated across time with other confounds. And I'm going to show you an example of that in the next few slides. But that can really complement the rest of the report to see if the network time course itself is confounded. Now, one last detail to better understand these outputs is that they are computed either from the pre-processing stage for the motion time course and the DVARS, or from the cleaned time series post-confound correction. So these outputs depend on how you apply the confound correction stage, essentially. Where here it's showing, of course, the clean time series themselves, but also more dual regression and the mask signal are computed on those clean time series. And the confound regression will depend also on what kind of nuisance parameters you selected. So if you provide the 24 motion parameters, then of course this variance explained will depend on the regression of those 24 motion parameters. But actually, if you also, what's important to know is if you don't apply anything, if you don't apply any confound regression, what will be done by default, it's still the regression with the 6 motion parameters, but without applying it. So it's just so that we can get at least an estimate of the time course from CR, from the 6 motion parameters, but your time series won't be regressed. So here, now I'm giving you an example of what can happen when there's actual confounds in the scan. Here I'm giving you a very obvious example of a scan that had some motion spiking event here, as clearly identified with the FD time course. We can see it's driving global signal fluctuation here. And at the end, importantly, we can see that our network time course in blue is clearly collinear with the confound time courses, showing that our analysis is very unlikely to be reliable. And so in those cases, we'll want to do some kind of correction. I'm going to come back to this in a few slides. So in addition to the temporal features, though, there's also a set of spatial features to this report, which help really to complement the temporal features in understanding what kind of confounds are present in your data more specifically, and also to see if your connectivity maps are representative of the network you want to image. So first at the top, and also all of these are derived from the clean time series. So at the top, is the standard deviation at each voxel. So similarly to the pre-processing stage here, it's just showing the distribution of signal variability. In the case of a good quality scan like this, it looks relatively homogeneous with no index of confounds. The next one is the variance explained by confound regression at each voxel. So you can see that in this case, there was a few index of motion which show around the brain and in the ventricles, although it's relatively minor for this particular scan. Then another important feature I want to highlight is this map here that shows the covariance with global signal. So it's a way to assess what is the global signal specific to, where does it load the most? And in the case of a good quality scan with clear network activity, it tends to load actually in the cortex, in gray matter region, as I'm highlighting here, with features that are reminiscent of certain brain networks. And that's usually a very good index. If you see this, that your scan is minimally corrupted and has nice network activity. And finally here, the network maps that you computed for your particular analysis are going to be displayed as well. Here, there was 3 different dual regression components. And in this scan, they were all specific to the prior IC component. Now, in contrast, coming back to our example of a motion corrupted scan, you can see how the features are drastically altered. Now your signal variability is really driven by motion contrast around all of the anatomical edges of the scan. Same thing for the global signal. Now the global signal is really representing these motion confounds. And at the level of your analysis, your connectivity maps are severely altered as well. So it's really the most obvious case you're going to encounter of an analysis that's heavily corrupted, and you should definitely not trust results coming out of a scan like this. So then what I didn't mention is that this particular scan, in this report, it was not corrected for anything. And you can see that none of the motion was really corrected for. And I want to ask you, actually, does anyone have an idea of what would be a good correction strategy to do in this case if we want to get rid of those confounds?
Yeah, censoring, basically.
Censoring, yeah. In that case, censoring would be really the main thing to do, because you have in that case the very drastic spikes from the frame-wise displacement time course here that are driving your global signal, and applying censoring will remove the biggest effect. Something I do want to detail about censoring is that in this report, you need to be aware that the scale in millimeter will be specific to your scan. If we go back to the previous example, you see that the scale here only goes to 0.03 millimeter, which is extremely low. So even if you see a spike here, it's not driving your signal really, and it's not a suspicious one. But in the case of the other one, it goes up to 0.6. So that's very high motion event. And so you just keep in mind that you need to look at the scale and for frame-wise displacement. And what I would usually recommend as a good threshold to be quite conservative is 0.05 millimeter. But I do recommend you looking at your data to judge what's a sensible threshold. And so what happens if we apply a good correction to this scan? Actually, we can really recover a very nice feature. So first in the temporal domain, we applied censoring. There's no more spikes that are present. And there was also some motion regression applied with 6 parameters. And you can see that your network time course doesn't seem to be really correlated very particularly with confound sources. If we look in the spatial domain, the variability map is more homogeneous. You have some nice gray matter contrast in the global signal, and your network components are much more specific to the networks that we were trying to model. So really in summary, looking at this report in detail across all your scans, hopefully can give you some intuition about what kind of data quality issues are present in your scan, what you should be careful about, and that can in turn inform what kind of confound correction strategy would be adequate. So for instance, if you see evidence of physiological confounds, I'm going to show you an example of that later. But in those cases, you might want to regress the white matter CSF of vascular mass signal. You might want to apply bandpass filter. In the case of motion, you should consider frame-wise displacement censoring, regression of motion parameters or aroma. If there's a lot of suspicious spikes in DVARs that are not due to motion, there's an option to apply a censoring based on DVAR as well. And if there's drifts, there's high pass. And finally, what I call a last resort, remove everything solution is global signal regression. So for those that know a bit about the confound correction literature, you'll be aware that global signal regression has been quite controversial for at least the last decade, no, even more than a decade, like 15 years at least. And that's because it's been very popular for confound correction because it's excellent at removing confounds. It's probably the single regression that will remove the most confounds. However, at the same time, as I've shown you, it can be related to network activity as well. Like I was showing you in the good quality scan in the global signal map, it was loading onto the gray matter with features of brain network. And it's been documented that it can actually remove some of your signal of interest in other papers, such as Bright and Murphy here, where overall, especially with the confound regression step, you should be careful not to overcorrect your data. The best strategy is not to just combine everything and remove as much as possible because you can actually remove your network signal. In particular, I would say with global signal regression and low pass. But if you're interested in more details on this, I invite you to check out some examples from the RABIES preprint or read this paper. And there's other papers as well. Yeah. So how are we doing?
11:23.
Okay, we're still good. So were there any questions for this particular step? Anything that wasn't too clear?
I guess more of like a kind of question for discussion. When you're approaching a data set, do you usually see that the same kinds of like problems or like indications that you need a certain kind of pre-processing occur throughout scans, or are there some data sets where it's like they're just extremely variable? Like one might have more motion, one might need like low pass filtering.
So I might be biased, but I've dealt with extremely variable data sets. I'm gonna cover a few more examples, but they can really range in the kind of problems they have. Sometimes there's no network activity, sometimes there's a lot of motion, sometimes it's more physiological confound. I guess that's the main observations I'd see, and they will manifest themselves in different ways. And yeah, unfortunately, there is some expertise in like looking at many scans and kind of recognizing when something is suspicious. But the more obvious ones will stand out, and they should be easy to kind of correct for. But yeah, in general, my recommendation is to look at your data, understand what is present, and apply a correction in consequence of that. Because there doesn't seem, in my experience, applying different type of correction will be good only for certain data sets, not for others. So there's always some kind of trade-offs at play. And the point, this is partly what led me really to develop this, is that I noticed these trade-offs and how just applying confound correction across the board was performing very poorly. And it seems that we need to have a more informed way to make decisions about how we address data quality issues. And so, yeah, overall, this first part is really trying to understand what is even present on your data. And the second part, I'm attempting to characterize whether we did a good job or not at the level of group statistics. And I hope that these metrics that I'm going to cover are a better standard to assess, okay, is that good enough of a correction or not? That's kind of the goal of the next section.
I guess kind of as a follow-up to, so if we're interested in looking at group differences down the line, as a lot of our projects are designed around, depending on like what kind of model we're looking at. I could imagine that there could be like differences within the mice, even in the scans, or in like what kinds of like artifacts appear. I wonder if there's like an interesting way to like look at some of the like internal steps here, like to see, I don't know, if there's like greater motion in like one group of mice than the other, or like in like some of the parameters that they need like correction on to assess, like as another like kind of, I mean, first of all, just so we know, in case like that could also be biasing any downstream results, but then also as like kind of an intermediate like outcome.
Yeah, definitely. It's a bit what I think I'm touching on in this section. I have, like here, I'm going to go through some recommendations in that respect of what kind of metric you could introduce in your analysis to see whether, let's say, your two groups are driven by a motion difference, your group difference are driven by a motion difference, and things like that. I want to say that definitely I would recommend to still apply always the same pre-processing across your groups, because if you apply 24 motion regression because one of your group has more motion, apply it even in your group that doesn't have as much motion, because who knows what kind of problem this could create for sure. But yeah, it's kind of the point of this. There's this kind of generic report that's generated for, it can be, you could generate it in each of your groups separately or across both of your groups together. But also there's a lot of outputs that are generated with this report, such as measures of mean formwise displacement, which you could load yourself. Like there's a bunch of CSVs with metrics you can load during your analysis and maybe control for it in a linear model as much as possible. Although, having said that, linear models don't necessarily correct well for those kind of problems. Ideally, they're not there to begin.
Sure.
So
at least you could test for it to demonstrate though that like if you do see group differences, that it's not due to these like inherent differences in scan quality.
Yeah. But so yeah, hopefully like by the end of that process, what you would have is you would have identified what the potential problems are. You would have metrics for them, and you would be able to well, I'm going to touch a bit on this, but correct your confound correction and really consider your analysis in consequence of what you've observed to control for those potential issues. That's really the overall goal.
Anybody out in cyberspace have a question regarding this analysis step?
Seems like we're good.
All right, we'll continue on.
So I move on to the next step, which is more about developing quantitative metrics of analysis quality control at the network level. So I comment about my decision here for design decision for these reports. They all focus on really analyzing one network at a time. And I made this decision because of interpretability. Essentially, we have access to more features that we can observe in the spatial contrast of connectivity when we look at a single network at a time. And so they're designed really for you to look at different regions of interest, see where in the brain you have pretty good mapping of brain networks, and hopefully that can inform your analysis. And yeah, I think it's going to become obvious why this is useful in the next few slides. In particular for that first metric here that I'm going to cover, which is interscan variability in connectivity. So essentially, we generate a map, a standard deviation map at each voxel based on the different network maps collected across scans. So we're just looking at the inter-individual variability. And now, why we might be interested in looking at this is because when we do a statistical analysis in most cases, such as a group comparison, this is essentially the driver of a result. It's going to be inter-scan variability in their connectivity profile. So depending on what are the main drivers of variability, is going to have an impact on what is going to be likely the driver of your statistical analysis. And what I'm showing you in that example here is with a data set that had a set of very specific maps that were minimally corrupted. And what we tend to see in these data sets is that the standard deviation is mostly specific to the regions of the network that we're imaging. That's an observation I've derived from looking at several different data sets. Whereas in contrast, for other data sets, such as some where there's no obvious evidence of network activity that was measured, their standard deviation map tends to be completely random. And in other cases where there's spurious connectivity with heavy corruption of the scans, then the inter-scan variability tends to be completely driven by other sources that are not specific at all to the network. So this is a very useful metric for distinguishing between different quality outcomes. And the way I've devised of really looking at how specific this variability map is to the network is to essentially threshold this map to highlight the peak voxels and then compute the overlap between this variability map and the thresholded map of the network we're trying to image with a dice overlap. So here I'm showing an example with this network, which is an IC component of the somatomotor mouse network. And essentially, I'm comparing the peak voxel between a prior map of this network and my variability map that obtained from my dataset. And that metric is going to be saved in the CSV file automatically when you generate this report. I'll show you later how you can find it. So this is the first metric of the report, but in addition to this, there's several confound metrics that are correlated with connectivity across scans. That's a pretty conventional way of looking at confound effects in the human literature, in particular with mean frame wise displacement. So these are correlation maps where, for instance, mean frame wise displacement was correlated with connectivity strength across scan. And that's an important complement to the first measure because in some instances, confound can impact the network amplitude, but not necessarily the shape of your networks. So you can have instances where you're going to see a correlation between the amplitude of connectivity and confounds without necessarily being able to detect it very well with this first measure. And so I have three main measures that I'm including for confounds that are complementary. So there's this direct measure of motion from frame-wise displacement, temporal degrees of freedom, where if you apply censoring, you might not have the same number of frames, and that can also impact connectivity amplitude. And the last one at the top here is derived from the spatial diagnosis report. It's the variance explained at each voxel from confound regression. So that tells you in a given scan where there was more amplitude of confound. And they're pretty useful for capturing certain types of confounds, like the example I'm going to show in the next slide. So here I'm showing you an example of the default mode network. So this is the prior IC component I'm showing at the top. And in that case, there was a high correlation in that feature within the network. So in fact, within the region, the thresholded region of this prior component, the correlation across scan was up to 0.4, which is pretty high. And to understand what was happening, there's a final output that I want you to consider, which is distribution plots, which are useful to detect some outliers or to visualize the correlation structure across your different scans. So these plots are essentially another version of these maps here, but instead of being spatially defined, they're more distribution plots to see the distribution of scans. So each point is a scan, and you have the different confound metrics, such as the variance explained from confound regression or mean frame-wise displacement as a function of network amplitude, which is actually the variance explained in the context of dual regression, or the network shape. which is very similarly computed with the dice overlap metric that I've shown earlier. And in the case of this dataset, what was striking was two clear outliers here in the metric of CR variance, where certain networks had high amplitude together with high variance explained from confound regression. And clearly they were driving some kind of correlation that I'm seeing here. So what I did was then go back to the scans and look at the spatial diagnosis report. And what I found is that, in fact, there was evidence of physiological confounds in these two scans, where there was a high loading onto the ventricles and major brain vessels in both the variability map and the global signal covariance. And these particular physiological confounds really overlap with the default mode network. And so that's why these two scans were driven by very high variance, or had inflated variance explained. And a way to correct for those confounds was to either apply a high pass filter in this case, or a white matter CSF mask regression was sufficient. So that summarizes really all the three different reports that you can use with the RABIES output and how they're kind of interrelated together. So there's not necessarily a linear step-by-step way to assess data quality. Unfortunately, you might have to go back and forth between the different reports as you try different confound correction strategy and try to gain a better understanding of what's happening in your analysis. So there's just one last comment I want to quickly make. There's another level of quality control that I would likely recommend in the future, because I've noticed that in some instance, the group statistics were missing very obvious failures that I was detecting at the scan level. And so with there's likely in the future going to be an upcoming feature to remove scans that have obvious problems, either in the context of network detectability, so whether the network shape is highly disturbed, or in terms of how the time course is correlated with confound components. So I won't go over the details, but here I'm showing a distribution of many different scans. Here were very highly corrupted scans. Here were scans with no network activity. So there was a way to try to classify which scans should be removed even prior to the analysis. But that's not currently implemented very well as a quality control step yet. So that sums up all the different aspects of data quality you can investigate with RABIES. And after you've gone through that process, hopefully you don't have too many problems, but if you do, you have to consider how you might be troubleshooting these issues. So the first thing really you'd want to look at is whether there's a sensible way to optimize confound correction, going back at the confound correction stage and rerunning the diagnosis again. So you can use the scan-specific report to see what kind of confound may be present, for instance, or otherwise, you might have to make specific consideration for your statistical analysis. So if you know that, if for instance, certain networks are good quality, but others are highly confounded, and you can't really correct for those other networks, you might consider having a specific analysis to only certain subset of brain regions, or otherwise you might need to use some of these metrics as covariate in your statistics. I'm not going to provide strict guidelines on this because I think it's definitely very much an open discussion of how we should integrate data quality issues into our analysis. Or otherwise, the very last resort, which I hope you won't face, is in certain instances, unfortunately, such as when there's literally no network activity detectable, which has definitely happened in our lab when I started my own grad school. There's really no way to study networks when there's no network to begin with. That can happen when either you have scanning issues or your anesthesia was too strong and disrupt the network activity in your mice or rats. And so in those instances, you really have to go back to the acquisition protocol and fix it. But hopefully this is the last result. Otherwise, that really sums up kind of the conceptual overview. I'm going to go over some more details of the execution and the outputs that you can look at. So first, the data diagnosis is computed at the analysis stage. So when you're running rabies analysis, there will be this option, data diagnosis, that you need to select to generate all these outputs that I just mentioned. Otherwise, you might want to consider scan list here, which is a parameter where you can specify which scan to include in the report, in particular for the group statistics. So in that way, you can either remove some outliers or consider only a subset of your data set if you don't want to compute it on all the scans. Other important inputs are these ones here that control the ICA maps. So prior map refers to a Nifty file that will correspond to the different ICA components that you're providing for dual regression. And then here you also need to specify the index for the network components and for the confound components. So I do recommend there is a default for the mouse brain provided in rabies that overlaps with the default template. But I do recommend that you compute your own ICA decomposition on your data set, because that way you have a data set a set of components that are more representative of your data. And then that leads to better quality outputs. And then another, I guess, more important input to consider if you're doing seed-based connectivity analysis is this seed prior list parameter, where similarly to how you need to provide prior network maps with ICA, you need to do the same for your seed-based connectivity map. So for instance, this will just be Nifty file that should be a network map. They could be derived, for instance, from an average across a data set that has decent quality. Essentially, you just want to provide a Nifty file that's representative of the network you're trying to image. So in terms of the output, there's going to be a new data diagnosis data sync folder that will be generated. And in these, there's going to be several subfolders. So a lot of the files that are displayed in the spatial temporal diagnosis are going to be saved into these Nifty formats or CSV, so you can consult them or use them if you will. But the main folders to look at for the context of quality control would be these two folders for the spatial temporal diagnosis and the analysis QC folder. So within these two folders, you have either the spatial or temporal features. It will be PNG images for each of your scans, pretty straightforward to go through. Whereas for the group statistics, you'll find this within the analysis QC folder, where you will have actually both a non-parametric and a parametric version of those statistical reports. But within each folder, you will have outputs for each of the different network analysis that you computed. So here I'm showing you an example where there was 3 different dual regression components, as well as 2 different seed connectivity analyses. So for each of these network analyses, you'll have the first PNG image that's going to be the thresholded maps like this, as well as the second one with the unthresholded version. And then finally, there's also going to be a CSV file that will have computed for you the dice over specificity of this variability map, as well as the mean correlation of these confound effects within the region of the thresholded network. And then finally, within this folder for accessing also the sample distributions, these images will be available as PNG. Similarly here, there will be a version for each of your different networks. And you will have with each PNG image an associated CSV file, where you will have essentially all of these metrics here that are displayed encoded for each subject. So that way you can relate which scan might be highlighted as an outlier to a subject ID into that CSV file. I'm going to show you an example just after this. So essentially for all of those different metrics in the y-axis and x-axis, you're gonna have the values accessible for each subject. So I'm gonna go quickly over actual output folders just to give you additional example here. Do we see it in the Zoom call?
No, you shared.
No, we don't.
You're sharing the screen, the other window.
Let's see here. So just opening the CSV file for the sample distribution. So what it looks like, you have your different scan ID, and you'll have the component variance, which was plotted, the dice overlap for network shape, confound regression, mean frame-wise displacement. And for each of these, you also have a binary output of whether it was classified as an outlier or not. For instance, here there was one that was an outlier in terms of mean frame-wise displacement. You can find which scan this was. And if I'm opening the image, you can see that it was this outlier that was seen in that particular image. If you want to go through your spatial diagnosis file, it's going to look like this. You open it, it's in the 3 slice orientations, and you can circle through your different scans to look at the quality. This is a data set that was very high quality. There's almost always very specific network maps, as well as nice Greenhunter contrast. Okay. So if there's no more question on this particular aspect, that really wraps up all the different aspects of the pipeline. So RABIES really aims to handle all of the intermediate image processing decision step for you and try to develop better standards for the community, all the way from pre-processing to analysis, data quality control. And as I've already said, this is a evolving software infrastructure, especially at the level of data quality assessment. It's still evolving. The paper is not out yet, but hopefully will be in the pipeline soon. But in the meantime, you can consult the preprint. And I just want to end quickly with a few resources. So you can find the preprint accessible on bioRxiv here. All the code is open source on GitHub. You can consult it. And if you encounter certain bugs or issues that you think can be relevant for the software, please raise them as a GitHub issue. It can be relevant for the whole community to have access to these issues that are arising. And if you have more open-ended discussion comments or questions on how to use the software or how to improve it, you can also post this as a discussion in the GitHub discussion page. There's a online read the doc documentation, which has a lot of the details that I've went through today and even more. So as a user, I highly encourage you to go through this. And finally, the different container versions are hosted on Docker Hub. You can consult them at this link. And finally, one important comment, we absolutely welcome contributions. If there's a certain feature that you think RABIES would benefit from, I invite you to comment it on GitHub. And even better, if you have certain scripts to share and you can add certain to the pipeline, you can submit a pull request on GitHub where we're going to review how to integrate this particular addition. And if you have some questions on how to do a pull request to make contributions, you can just reach out and I'll give you the details on that.
Gabe, am I correct that the preprint will have an update soon?
Well, likely, yeah. Likely will be updated.
So for the audience who's already read the preprint, there's likely to be kind of a new version of that coming out soon. It has a lot of the things that have been shown here integrated into it.
Yeah. So most of what I've covered today, except maybe for the distribution plots at the end, are in the preprint as is. But there's definitely additional detail that are in the preprint on how I came up with these metrics and the justification for why they were selected in more details, and some observation on how different dataset performs in terms of data quality, how correction can influence these outcomes. So I also invite you to look through that.